Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary of the CCQTA and Principal Consultant at Omnicon Consultants. This episode will focus on water and crude oil. In this episode, we're going to focus on the following. What are the different types of water when we're considering the water content of a crude oil? What test methods are employed, including their capabilities and limitations? Some comparative testing and how different test methods can yield different results on the same sample. Then a brief discussion on sample handling. And then finally, choosing methods that are fit for purpose. There are three different types of water you'll find in crude oils: free water, emulsified water, and dissolved water. Let me show you an example to understand these a little better. A common sediment and water test uses a centrifuge to separate oil, water, and solids, or sediment, based on density. When looking at the tube, you have three phases. These include solids, free water, and oil. Free water is water that readily separates from the oil and will settle in tanks, low spots, etc., but overall is pretty easy to get out. Now let's look at the same tube under UV light. Under UV, another phase is revealed hidden between the water and the oil. We call this a midphase. This phase contains emulsified water as well as waxes, asphaltenes, resins, and fine solids. These stabilize the emulsion, making it neutrally buoyant between the water and oil phases, so this also means this layer goes undetected by centrifuge methods, so this water is hidden. This emulsified phase also can be augmented by additives such as polymers that are used in drilling, fracturing, and other oil field operations. For example, polymers are added to increase viscosity of the water-based drilling fluids to move solids out of the borehole during drilling operations. Lastly, although water is mostly miscible in hydrocarbons, it does have some affinity for aromatics, alcohols, aldehydes, etc., so some will be dissolved in the crude. It's typically in low ppm levels, but still present. However, it is also not accounted for using the common centrifuge methods because it's not observable. Now let's look at the methods for water content measurement that are readily available. There are currently 6 test methods commonly used to measure water in crude oil. The first 2 use centrifugal force to separate the phases based on their density, as I'd mentioned before. These methods require the phases to be visually distinguishable from one another so that they can be measured using the scale on the tube. This is why both emulsified and dissolved water are not detectable using these methods. The next 2 involve chemically reacting with water via the Carl-Fisher titration. All types of water react with the titrant, therefore free, emulsified, and dissolved water are all quantified. The last 2 employ distillation to separate water from the hydrocarbon. Since all the water undergoes a phase change during the distillation, it is separated from the bulk crude. That includes any water that was previously dissolved and or emulsified. The vaporized water is then condensed along with light hydrocarbons of lower or similar boiling points, and then the water and light hydrocarbons easily gravity separate and make quantitation simple. Both ASTM D4007 and API 10.3 and 0.4 also measure for sediment. This is one of the drawbacks of both the Carl-Fisher titration and the sediment method, is that they do not quantify the sediment. To produce a typical sediment and water number, or S&W, the solids must be performed separately and the 2 results combined. The most common sediment method is ASTM D4807, sediment in crude oil by membrane filtration. Solids quantitation is covered in much more detail in the CCQTA Lunch and Learn on filterable solids. I do want to caution users on the quantitation accuracy of the 2 centrifuge methods, given that the solids are measured visually based on the reference scale on the centrifuge tube. As you can see from the image, the scale has limited demarcation at the bottom of the tube, so the solids value is more of an estimate than a hard value. Functionally, the method is intended for water, but it would also be obvious if there was a significant solids present that would be problematic. The specifications are commonly 0.5% S&W, but if the crude contained more solids than water, there would be a serious problem. The D4807 method, on the other hand, is a physical measurement of the solids captured from the crude oil, accurate to the parts per million level. Now let's move on to look at the test methods in a little bit more detail. I showed you 6 different test methods, but they can all be combined into 3 categories: centrifuge, Carl-Fisher, and distillation. Let's start by summarizing the centrifuge method. The centrifuge methods are the most commonly used for both production, water cut, as well as custody transfer applications. The basics of the method is that 50 ml of freshly homogenized sample and 50 ml of water-saturated toluene are added to a centrifuge tube with a couple of drops of demulsifier. Then the tube is stoppered and the mixture is inverted 10 times to mix. Two identical tubes are prepared at the same time so as a duplicate sample to balance the centrifuge as well as for results comparison. The mixture is heated to 60 degrees for 15 minutes. Then the tube is centrifuged at 60 degrees for 10 minutes. Then the water and sediment are measured and recorded. The cycle of centrifuging and measurement is repeated until the combined volume of sediment and water is constant for at least 2 consecutive readings. The sum of the water and sediment are reported as the percent sediment and water, or S&W. Now let's move on to the Carl Fisher. Of the two Carl Fisher methods available, D4377 and D4928, 4928 is the most common. This method also includes 3 different procedures. There are variations in the different procedures, however all 3 are based on the same reaction and detection method. Procedure A reports on a mass percent basis, while Procedure B on a volume percent basis, however both involve the same direct injection of sample to the titration cell. Procedure C is different from A and B in that it uses evaporation to drive the water out of a known mass of crude in a vial, and then that water vapor is swept into the titration cell carried by an inert gas like nitrogen. This method also reports on a mass percent basis. Now let's look at a couple of examples of the procedures. The titration cell is the same for all 3 procedures. Water from the sample dissolves in the analyte solution, in this case hydronal, containing lithium iodide, sulfur dioxide, methanol, and a base like imidazole. This triggers the electrochemical generation of iodine at the anode by oxidation of iodide ions. The iodine reacts stoichiometrically with the water in the presence of sulfur dioxide and the base, completing the Carl Fisher reaction. The reaction consumes 1 mole of iodine per mole of water, and the titration continues until all the water is reacted. Once an excess of iodine is detected, indicating the endpoint, the instrument calculates the water content based on the total charge passed. The cathode compartment, separated by a diaphragm, contains a conductive catholyte with lithium iodide in methanol to complete the electrical circuit and allow for hydrogen evolution. Procedure A injects a known mass of sample into the cell, while Procedure B injects a known volume of sample. Procedure C uses a known mass of sample in a vial and places it in a heater block where it heats the vial to evaporate all the water from the sample. The water vapor is then swept from the headspace of the vial into the titration cell for quantitation. This method has an advantage that the crude oil is never injected directly into the solution, so the solution lasts considerably longer. If the sample collection is performed in the field using pre-weighed vials, then homogenization is also not required because the whole sample is used for measurement. The distillation methods utilize the boiling point of water versus the bulk crude phase, as well as the immiscibility of water in hydrocarbon solvent to isolate and quantify the water content. Like the Carl Fisher titration, this method quantifies all types of water simultaneously. First, 50 ml of sample is transferred into a graduated cylinder and then to a distillation flask. Then xylene or another suitable solvent is used to rinse the graduated cylinder several times with the solvent, which is also then added to the distillation flask. Then heat is applied to the flask and the solvent and water are boiled out of the sample until the water level in the sidearm is constant. The volume of water is measured using the graduations on the sidearm. When ASTM publishes a test method, it provides important information prior to outlining the procedure. Along with the designation number, which includes the publication year, it also describes the method's use, scope, and possible interferences and other special considerations, if applicable. This is important information which end users should review prior to choosing methods for sample analysis. ASTM also provides a precision and bias statement for their methods, which includes repeatability and reproducibility statements. Finally, proper sample collection, handling, and subsampling is quite important when undertaking water and crude testing. Let's look at what I mean by precision. Repeatability is the difference between two results obtained by the same operator with the same apparatus under constant operating conditions on identical test material, so the same sample, would, in the long run, in normal and correct operation of the test method, exceed the following value in only one case in 20. So effectively, this is the same person, same lab, same test, same material, run in duplicate. Next, we have reproducibility. The difference between two single and independent test results obtained by different operators working in different laboratories on the same test material would, again, in the long run, in the normal and correct operation of the test method, exceed the following value in only one case in 20. So this effectively is one lab versus another lab, comparing on the same sample, but using different instruments, different techs, so on and so forth. The repeatability and reproducibility values allow users to assess precision when comparing results generated by duplicate results or between different facilities. These values are important as they identify the capabilities of individual test methods and provide users with insights as to the hazards of comparing data from different test methods. Now let's look at the repeatability provided for 5 of the 6 ASTM methods. This chart shows the variability one can expect from one lab running the same sample in duplicate, assuming the same operator and equipment was used. You can see the wider spread, or the plus-minus, of the centrifuge and distillation methods have compared to the tighter spread of the 2 Carl Fisher methods. This chart highlights the superior precision of the 2 Carl Fisher methods over the other 2. While internal improvements may help a lab be more repeatable, it does not address comparisons to other labs. This is where reproducibility comes in. As to be expected, the variability in results increases when comparing one lab to the next, since more variables are factored in, such as different operators, equipment, calibrations, etc. This chart is similar to the repeatability chart in that the centrifuge and distillation methods have a much larger plus-minus than the Carl Fisher methods. This highlights the hazards of directly comparing data from different facilities as well as from different test methods like the centrifuge versus Carl Fisher, since they are not based on the same detection methods. Comparing two different methods is like comparing gala apples to crab apples. They're both apples, but they both taste very different. The magnitude of the site-to-site precision also helps explain why there are frequent arguments between parties as to the accuracy of the measured values, particularly during custody transfer. Compounding the problem, as we discussed earlier, is the fact that methods differ in their ability to measure the different types of water found in crude. Finally, water is not uniformly distributed within the crude, which creates additional issues during sample collection. Sample handling, including collection, homogenization, and subsampling, are critical to ensure the success of any analytical test. If a sample is sampled incorrectly or handled poorly, the results of any subsequent testing are going to be wrong or misrepresented. Water is normally dispersed in the oil as free or emulsified water with varying droplet sizes. Therefore, collecting a sample of flowing product at various time intervals would not be expected to provide samples with exactly the same content of water. Imagine you have a flowing pipeline that we're going to sample. You take one sample at 8 a.m. and then you take another at 8 p.m. When you measure the water content, you get two different results, with one at 0.08% and the other at 0.04%. Which one is representative of the product? In fact, both are representative of the product at that point in time. These are called spot samples. Now, if you wanted to know the composition over a broader period of time, you could take those two results and average them. Then you could say that over a 12-hour period, the water content was 0.06, or even better, you could just mix those two samples 50-50 and measure the water content of the blend, and you would still get the same result. That is the concept of the composite sample. It is a collection of many samples taken over a period of time to provide the average of the whole. Now, typically, a composite sample is comprised of many samples taken at specified intervals to represent a product. This may be on a batch basis to monitor the quality of different products, or it's over a period of month to monitor the overall composition of a single stream. With many samples, you can have a reasonable confidence if you captured a reasonable representation of the product that flowed from time A to time B, or say 0 cubic meters to 300 cubic meters in the case of a batch. For this reason, daily composite samples and not spot samples are normally collected at production facilities and tested for custody transfer purposes. Some things to remember when sampling and testing for water content. Water dispersed in oil is a heterogeneous mixture. The water content in the oil will vary within a flowing pipeline. Composite samplers are recommended for water content in flowing streams. Variability and stratification also exist within a composite or spot sample, so homogenizing samples prior to subsampling and testing is extremely important, especially when subsampling involves very small volumes, like a syringe. ASTM D5854 provides direction on sample mixing prior to subsampling for testing purposes. And lastly, to ensure a sample is homogeneous and subsamples are representative, many laboratories will collect and test multiple subsamples, especially when very small subsample volumes are collected, such as in the D4928 procedures A and B. There are a couple other water content methods that get discussed from time to time. ASTM D6304 is another Carl Fisher titration method and is effectively the same as D4928 and does include the same three procedures. ASTM D7546 utilizes a relative humidity detector instead. Both methods were developed to measure water in finished products like biodiesel, lube oils, and additives, and neither of the methods are scoped for crude oils, so caution should be taken if you ever use them for crude oil. There are also several technologies that are used for online measurement in truck loading and unloading facilities, pipelines, marketing, and storage terminals. These are usually coupled with occasional sampling and testing and are intended for water cutter monitoring as opposed to custody transfer applications, although there are applications where it does get used for custody transfer. Since performance and measurement accuracy can vary with the sample matrix and the water content, technology selection is quite often application specific. This chart provides a comparison of 66 D4007 results with online measurement at truck loading facility. Water content in these locations can vary from less than 1% to as much as 100%. This facility inputs data from both capacitance and microwave measurement technologies and a number of other critical process variables into an application-specific software, which then generates the data required for custody transfer. Measurement accuracy is reported to be 0.1% for water below 5% and 1% for levels up to 100% and is deemed acceptable for custody transfer at this location. In this case, water content at or below 5% are measured by capacitance and above 5% by microwave on two separate instruments. The results are plotted against one another to make it easy to visualize differences. If the results are exactly the same, then they should appear on the quality line. If one value is higher or lower than the others, it will deviate from the line. This plot is a little hard to see the variances, so let's look at it scaled a little differently. I've narrowed the scale to show the results below 14%, though it's easier to see the variances. You can see many of the results are below the equality line. These two stand out because they're the furthest from the line. In this case, the online method reports results around 6.5%, while the results by the centrifuge are around 4%. This shows a clear discrepancy between the two methods. When I look at this data overall, there are very few points above the line, implying the online method typically reports similar or higher results than the D400 method. Of note, the cut point between the two detection methods is 5%. Let's look at it on the other end of the scale. The upper end of the scale has a bit more of a statistical distribution with points on both sides of the line. No specific bias is indicated, but also shows that few results are actually in agreement. In recent years, some CCQTA members have experimented with D4007 variables. For example, the centrifuge rates, demulsifier or knockout drops, solvent preparation, etc., all to help address reported discrepancies between methods and locations. Additionally, for this kind of work, they will often enlist the help of other industry members to collect both repeatability and reproducibility data on their investigation. The following two charts provide examples of this kind of work. In this example, the differences between Carl Fisher and centrifuge data are compared. The same produced crude was tested at two different labs, in this case, a producer lab and a pipeline lab. One can clearly see how much more water is detected by Carl Fisher and what type of site-to-site variability can be expected with the D4007 centrifuge method. A midstream company was enlisted to participate in this investigation. Again, the same produced crude was tested using both centrifuge and Carl Fisher methods. As was the case on the last chart, the Carl Fisher results consistently exceed the centrifuge results. This data also shows the magnitude of site-to-site variability. In general, fit-for-purpose requirements coupled with logistics and cost considerations dictate what test methods will be employed at various locations. For example, a production facility or battery will install and use centrifuge method for regular testing of oil to help optimize treater operations and emulsifier usage. The same equipment will also be used for sales oil quality. Downstream locations, pipelines, etc., may also use centrifuge methods. However, as their interest in quantifying all of the water, including emulsified water, increases, they may either refine the centrifuge method or move to the Carl-Fisher method. Refiners usually have an interest in capturing data on free, emulsified, and soluble water since its impacts are seen in desalter operation and plant water balance. In most cases, they prefer Carl-Fisher testing. Let's look at some key considerations when considering sampling and testing for water content. It's important to consider the objectives of testing when selecting a test method. From a custody transfer perspective, all types of water are important as you progress from production to the refinery. However, production testing is intended to optimize treater operation and is not concerned about soluble water since there's really nothing they can do about it anyways. Similarly, pipeline operability concerns such as freezing or corrosion are connected to separated water, so again, soluble water is of little concern. However, emulsified water may still cause issues. Refiners, on the other hand, are very interested in capturing emulsified and soluble water, the former because it can highlight potential desalter problems, and the latter because it will impact plant water balance. Water separation can occur during pipeline transport, particularly if flow is slow or interrupted. Composite samples then provide a better measure of the water content of the delivered batch. Water and oil are immiscible and they will separate, so the choice of sampling point can also be impactful. Choosing a sample point that is at the bottom of a pipe also means that water preferentially collects there. So proper sample homogenization is critical, regardless of the test method employed. It's important for both those running the test as well as those evaluating the data to be aware of the scope and limitations of each test. And finally, when comparing data from different sites or locations, the same test method should be employed since these can measure different types of water, and the user may not be comparing apples to apples, as we discussed earlier. Consider this when comparing centrifuge to Carl-Fisher results, that the centrifuge results will always be lower. D4928 Procedure C was developed with a unique process flow in mind. First, pre-weigh a septum vial at a central location, say a field or a commercial lab. Send those vials to various locations where custody transfer samples are currently collected in bottles or cans. Fill the vials in duplicate from the source during truck offload or from a treater or a tank, etc. And then return those vials to the central location. Weigh the full vials and load them into an autosampler. Perform D4928C on the whole batch of samples overnight and come back the next morning and review the results. This process flow eliminates any of the issues with homogenization because the whole sample is used, so all the water detected is related to the original mass of the sample in the vial. Sampling in duplicate and or triplicate also allows easy storage of retained samples should they be needed in the future. Since only about 20 ml vials are very small, many retains could be stored in comparison to 1 liter bottles. What this process flow also allows is centralizing instrumentation, calibration, and QC, which leads to better data. A wider adoption of this protocol in an area would allow multiple producers and midstream in an area to centralize testing and reduce disputes over water contents. That's it for this episode. Thanks for watching, and I look forward to connecting again. If you'd like further information about this topic or any other topics that CCQTA is working on, please visit our website at CCQTA.com. If you have any feedback, please send it to secretary@ccqta.com. Please check back regularly for new additions to our Lunch and Learn series and other videos.